Hi everyone, and welcome to the 16th TIA Centre seminar of the academic year. So my name is Adam Shepherd, and I'm a postdoc here at the TIA Centre. For those that are new to our seminars, we invite researchers and leaders in computational pathology and associated areas to discuss their work. And today I'm absolutely delighted to introduce Professor Jakob Kather. Professor Kather holds dual appointments in medicine and computer science at the Technical University Dresden, Germany, serves as a senior physician in medical oncology at the University Hospital Dresden, and holds an additional affiliation with the National Centre for Tumour Diseases in Heidelberg. His research is focused on applying AI in precision oncology. Professor Kather's research team at TU Dresden is using deep learning techniques to analyse a spectrum of clinical data, including histopathology, radiology, textual records, and multimodal datasets. Guided by the belief that medical and tech expertise need to be combined, medical researchers in his team learn computer programming and data analysis, while computer scientists are immersed in cancer biology and oncology. And the title of Professor Kather's talk today is AI Agents in Oncology. So Jakob, thank you very much again for agreeing to join us and give this talk. And when you're ready, please feel free to start.
Thank you very much. Thank you very much for the kind introduction. And hello, everybody. Good to see you all. I see many familiar names here. So I'm really glad that you took the time for this seminar. First, a few disclosures. I'm not a pathologist. I'm an oncologist actually by training, and lead an AI research group here in Germany. We have done image analysis and computational pathology for many years, and I have also presented here, I think at least twice in the TIA seminars about our work in computational pathology. So I thought that today I would really like to speak about something else that I think will be very, very relevant for all of us. And that's AI agents. I do realize that most of the people here specialize in image analysis and basically do image analysis the whole day. And this was true for me as well. My research group was fully computational pathology until some time ago. But now I do think that this field of AI, large language models and AI agents is evolving to such a degree that it will and is already impacting our work in computational pathology. So I would like to take maybe the next 25 to 30 minutes to present to you how I see the field of large language models and AI agents through the lens of a computational pathology researcher. And then I hope that we can discuss how you think this technology affects the way we do our work. Maybe some of you think that it is not changing the way we work and that we should focus on computational pathology directly. Others might think that you can combine it. So I'm really, really curious to hear your feedback. As I said before, I have the chat open here. So please feel free to put comments or questions in the chat at any time, or raise your hand or just speak up if there's anything you want to share or ask. Okay, with that, let me get started. Here are my formal disclosures. So I'm an academic working at universities and just have basically very minor additional engagements, including in spin-off as an advisor for spin-off companies that were launched by students of mine from our research group. And then let me take you to my most important slide, I think, for today, and that's how I see the history of artificial intelligence in cancer research. How I see this basically evolving over the last decades, let's say. Let's look in the past. Let's look in the past. Let's look to the very left-hand side. And what defined our research for a long time was to have a specific problem and to have a specific data set, and then using machine learning to solve this problem, right? So our tool of choice in the last couple of years was deep learning, and deep learning was really powerful for these types of problems. Let me give you some examples. You want to take chest x-rays of patients with COVID, and you want to predict whether someone has severe or non-severe COVID, right? You could do this easily by deep learning. Or another example, you have pathology slides of colon cancer patients. You know how long basically everybody lived until they got a recurrence of their disease. Well, then you were able to train a deep learning model to predict exactly this from the slides. Or your problem is that you have a certain number of prostate cancer, of prostate biopsies, and you want to determine which of these have cancer and where. So then you train the model for specifically this. And this field is basically now well established. And from a technical point of view, we can even say that it's plateauing, because the incremental benefit that we get by applying newer methods on the same data set, if we have these types of well-defined questions, the incremental benefits are really, really getting small now. So on the other hand, working in this area of single domain, single purpose models is still very important, because this is how our medical device approval works. So if you ever have the idea of getting your work to the patients, then you have to have one specific purpose, one specific very well-defined purpose for your software. But from a technical point of view, this is basically our baseline, what we can really do well now, and we have the tools and we know how to approach these problems. Well, let's advance a little bit in time towards a slightly newer technology, multimodal models, where you have one single deep learning model that takes different types of data as an input, for example, images plus genomic data. And there have been very nice publications in the last couple of years that have shown an added benefit of combining two different types of data in some circumstances, right? Sometimes there is no benefit, sometimes there is a bit of benefit. You really have to try it out. From a technical point of view, there's multiple ways of approaching this multimodal fusion problem. For example, there's early, mid, and late fusion, or there's basically fusion in different types of domains. For example, in the latent space, are only using features that were previously extracted, etc. So there's many ways of how to approach this problem. The practical limitation here was always to get enough data, to get enough patients with all of these data modalities present. Well, let's go a bit further in the history of AI in cancer research towards foundation models. Foundation models, of course, have been transformative for our field, and specifically for computational pathology. Now, everything is, of course, based on foundation models. We never train a model from scratch for any computational pathology task. We always start with foundation models that were trained with self-supervised learning on a large amount of non-annotated or sparsely annotated data. For me, the main implication of foundation models is that suddenly all of the data that we have available that we never thought were useful, for example, all the images in a pathology department without being linked to any clinical outcomes or any clinical information, they were previously useless for us to train anything, because we always needed these labels. But now, in the age of foundation models, we just can take 1 million or 10 million slides, work on them with self-supervised learning, to create a foundation model that has good representations, and then we can use this to fine-tune it for downstream tasks, or to put another model on top that uses the learned representation. So foundation models have been really, really important, but now there's, of course, two other types of technologies evolving. One is generalist models, and I'm talking about large language models here, because if you take a foundation model and you train it also on text, then you obtain something that is called zero-shot application, right, where you do not have to train any downstream models. You can just directly interact with the foundation model through language and directly apply to certain tasks. And then I will speak about this a little bit more in my talk. And then the latest addition to this evolution, in my point of view, is AI agents, where you take large language models and you couple them to other pieces of software. And this is, I think, where we are headed for basically everything that we are doing. So Sorry, this was quite a long introduction, but this is basically how I see our research evolving over time. Of course, it's important that we stay solid in these established niches, and these tools are certainly very important in many circumstances. But now I think we have to be aware of the new abilities that these later technologies, including AI agents, bring to us. So let me start to speak a little bit more about the large language models. Large language models, of course, are very simple in principle to train. Basically, you obtain all the text data that you can get from the internet, and you train with self-supervised learning. Um, Train a large transformer with self-supervised learning on it to predict the next token, right? Then it's being refined with reinforcement learning from human feedback or other techniques. And then ultimately you have conversational models such as the GPT models. What I find very interesting is that these large language models were improving really fast. So basically when GPT 3.5 came out, it was super simple to identify a breaking point where an example where the model just gave you a silly response. But that's not true anymore. Now you have to work really hard to get the model to give you some output that's really stupid. And also in terms of benchmarks, of course, these models are becoming really good. Let me just give you one example on the ARC AGI benchmark, where basically logical thinking, for example, in visual puzzles, as shown here, is being tested. And AGI was initially predefined at having 85% on this task. Well, now O3 High model by OpenAI basically beat that predefined cutoff. I'm not claiming that these models have reached AGI, but we certainly need to think about our benchmarks, and these models have become really good. What does it mean for us in healthcare and life science research? Well, it means a lot, I think, because large language models can be used for many different purposes. We have summarized recently all the areas of applications where we think that they could be applied, and basically categorize them into research, education, and patient care. And I do think that in all of these, there's a lot of applications. I will not go into this in detail, but please feel free to look it up. Also, another principle that we postulated like 2 years ago that I still think is true is that large language models are best used not as knowledge databases but as reasoning engines, right? If you want to know who was the, I don't know, 31st president of the United States, or you want to know who was the King of England in 1850, right? Something like that, where you are querying facts. Well, then I would suggest that you go to basically Wikipedia or somewhere to look this up. You don't really need a large language model, and you always have basically the danger that they might be hallucinating. However, when it's about solving problems and combining different pieces of information, then Wikipedia doesn't help you, but large language models do. For example, if you want to summarize documents, of course. Let me give you some examples for the use of like commercial large language models in medicine. Of course, you can ask a question like, how do I treat a certain patient with a certain cancer? And even ChatGPT 4.5 will give you a reasonable response. But then if you ask it, what is the knowledge cutoff, which will tell you October 23. So these models are basically outdated, of course, by design, which means they're not to be used as knowledge databases. And the way that you can use them to retrieve knowledge is if you provide the additional knowledge. Either you give the model basically access to everything, to the whole internet, but this also has certain dangers, or you provide, for example, the guidelines. You provide the breast cancer guidelines that you accept as the ground truth for breast cancer treatment, and then you ask a question about these guidelines. And in these cases, these models rarely hallucinate and often do a good job, even if it's a needle in a haystack problem. And we have recently compared this and found that these models are really good in these in such tasks. Other tasks that are of interest to the research community and the clinical community, although they are pretty boring, they can be hugely the large language models can have a huge practical implication here. And one task is information extraction. In pathology departments, for example, let's stay at the example of pathology departments. Even all the information that is in the reports is basically unstructured or semi-structured. And if you want to basically do any scientific analysis, for example, you want to ask for the last 10 years, for all the lung cancers that were processed in a certain pathology department, how many of them had a testing for ALK fusions, and in how many of them was the fusion detected, right? This is an incredibly difficult problem because just by regular expression matching, it's very difficult to find all of these cases. Of course, because of the different ways of writing down basically anything in human language, and also because of typos, etc. So large language models understand context and can therefore be used to extract such items. And we and others have shown this, and we have basically published also an open source tool based on locally deployable models here in that paper, which you can use for exactly these types of tasks. It comes with a user interface. Please try it. You can just use basically, if you have a set of 10,000 PDFs of pathology reports and you want to extract TNM stage, the biomarkers, etc., just use our tool. It's open source. It has a graphical user interface. It can use any, like, for example, Llama 3.3 model that runs locally on my MacBook Pro. This runs pretty smooth, and then you can extract these items from your PDFs. So this is an application which I think large language models have enabled, which previous methods did not enable us to do, but which are potentially very useful also for computational pathology studies, because in many cases having annotated data is the bottleneck. So imagine you have 1 million slides with the pathology reports and you want to train computational pathology models on this. Well, then the way to go is to first process it through large language models to get your ground truth and then train on that. I think that would be a perfect synergy that we have seen almost not at all in the literature, that I hope we will see much more. From a clinical point of view, again, one of the applications where we think that this is especially important is a very boring task called medical coding, where you basically for each patient have to write down ICD-10 or OPS or other codes, so you can claim the reimbursement from the insurances. Well, this is typically done by humans and is now also doable by large language models. Let's briefly look into another extension of large language models, vision language models. Of course, this has been a tremendous step that many of these large language models also can handle, were trained basically on images and text, and most frontier models are now multimodal, right? The ChatGPT models, GPT-4o, for example, you can use it to basically just ask a question about a pathology image. And I just put this random example here where the model describes, like zero shot describes a tissue, and I'm not saying that this is correct, right? Probably this is useless or not, maybe also not all the details are correct, but just having access to such models that have been trained on all of humanity's knowledge, of which pathology knowledge is a subset of, right? And then a description of these images from these models. I think this is super impressive. And again, for computational pathology research, I think this should be a baseline in our studies, right? If you are putting out a new model to detect prostate cancer in pathology slides and you measure a certain performance, well, then compare it to GPT-4o. Just compare it, give it the images, ask, is there a tumor in it, yes or no, and then you will get a baseline. And probably your model will be better than that baseline. But we have to try it, because sometimes our custom bespoke models are not better than these visual language models at baseline. And then we really have to reconsider what is the best approach. Of course, also my friend Faisal and his group has published, that's already now almost 1 year ago, where they published PassChat, a vision language model specifically for pathology. I'm not going to go into this like in detail. Of course, they showed that this outperforms general purpose vision language models and was a super impressive achievement for our community. Just again, from coming back to a clinical point of view, I just want to say that there's now efforts ongoing in our professional society, ESMO, the European Society of Medical Oncology, where we are trying to categorize the use of large language models in clinical practice of oncology. If you are ever doing research on a clinical application of large language models in oncology, or even in pathology, evaluation of vision language models or something along these lines, please consider to look up this LCAP initiative to see basically what is defined here as basically the minimum standard for validation items that we in ESMO recommend to follow. I will wrap up just speaking about large language models with basically outlook or prediction that soon large language models will nowadays large language models are better than human doctors at some tasks, but soon large language models will be better than human doctors at any task. I'm not putting a year on this. Right soon might be at some point in the future. But I think we have something that's really qualitatively different than we had before, and there is increasingly good evidence emerging. I think we cannot claim, seeing these evidence, we cannot claim that large language models are a hype. For example, look at this paper here, which is one of my favorite papers, where they showed that in a randomized prospective trials that a large language model chatbot helps patients with mental health issues like a psychotherapist. And this trial was a prospective trial that met its clinical endpoint. So, I mean, here we have the proof that large language models are helpful for like patient outcomes. And I hope that we see much more trials like this in the future. And it's just like very impressive how far the field has come. With that, I want to go to the topic that I'm most excited to share with you today about AI agents. So the main problem of large language models is that they can reason, but they cannot take action. Okay, I can, for example, ask ChatGPT or another large language model, how do I get from Dresden in Germany to Warwick in the UK? Well, then it might tell me different options that would be usually correct, especially if the model has access to the internet. For example, it might tell me you can take a train, you can take a flight, and then a train, you can take a flight, and then a car, whatever. But it cannot basically book the ticket for me. And that's the difference of AI agents, because an AI agent is very simple, is now, well, we now would define it as a large language model that has access to an external environment through some sort of interface. For example, it can just control a web browser. And then if you give it your credit card details, it would be able to not just find the best option to go from Dresden to Warwick, but to actually book the ticket. And this is technologically feasible. Basically, here a large language model that has access to different tools is how we now would define agents. Tools could be basically a knowledge database or memory or any other software like a web browser. Of course, for all the machine learning people here, basically there's this ancient classic textbook on artificial intelligence, and actually they define AI research as the study and design of agents. And agents can perceive their environment and act upon it. Well, if you are really minimalistic, then also a thermostat controlling your air conditioning or your heating is an agent. But of course, this is severely limited, right? Now, if we place an LLM in an agent system, these become suddenly super powerful. And of course, outside of outside of research community, these agents have already reached product stage, for example, um, in the field of software development, where there are several platforms that can really that use AI, large language model based agents to create complex software. And it's actually fun. I played around with one of these for a while. It's pretty good at, for example, building an interactive website, even with a database in the back end and with authentication and a nice front end, etc. All of this built by an agent, and it actually works pretty well. Of course, this is not going to replace engineers. Software engineers yet, but there's really some tasks where this works really well, and is a lot of fun. So I would encourage you to play around with this. Also, agents are helping us to solve medical problems. There's this very interesting benchmark that I'm sure all of you are aware of, Humanity's Last Exam, where last year it was basically observed by this group that the benchmarks are saturating. They're not useful anymore to distinguish different the capabilities of different large language models. And then they came up with super difficult questions that less than 5% of the current large language models, so the current large language models had a less than 5% success rate on these. Interestingly, there are some medical questions in this data set related to breast cancer, and I have just taken this question here from this data set, from the public part of this data set, where they have like a huge description of a medical case, which goes on and on, and I've even shortened it by at least half, and then you have a response basically, and this is so super difficult that like GPT-4o gets like 3% right, but if you look here, the OpenAI Deep Research, which is just a large language model with agentic capabilities. So it was able to iterate over, it was able to extract information from different sources, it was able to iterate and got over 25% right. So agents can also help with very different difficult questions, which I found fascinating. We have built, so Dike Ferber from my lab has built a prototype for a tumor board agent that is currently in press at Nature Cancer, where we just use a large language model. So imagine you have a patient case, a description of a patient, and you have the pathology slides and the radiology images. And now you want to basically simulate the tumor board, and you want to come to a recommendation based on these data. Well, one way to do it is you train a huge multimodal foundation model on pathology slides and radiology images and genomic data and electronic health record. And then basically you use this huge model, and then when you have a new case, you apply it zero shot and you immediately get a prediction. Well, this is very difficult. You need a lot of data to train this. And we are not able to do this actually practically speaking right now. But you don't even have to do it, because with an agentic workflow, you can do this with very lightweight components. You can have a large language model at the core. You can have a pathology image processing module that the agent calls. You can have a radiology module where there's radiology image processing models that the agent calls, and then it will be able to iterate and repeat and look at all the data and then give you a response. And we validated this actually to compare to human doctors and found that it was very good. So stay tuned for this. Another way that I'm even more excited about is, and that's still unpublished, is we built an agent that can make decisions for medical cases in a simulated electronic health record. So you have a patient coming with a certain complaint, and then a series of actions is taken typically, right? Maybe a biopsy is taken for the pathologist to look at an image. Well, usually not at the first step, but at the first step, maybe you would take a radiology imaging or a laboratory test or both. And so any type of like workup, diagnostic workup requires a different sequence of tests. Well, here we use the large language model-based agent to work its way through such medical cases and gave it the option to run such tests and then to get the results back from the environment. And this is and what we found is that these models are actually really, really good at planning complex diagnostic cascades and then also executing them. Of course, this is very interesting from a medical doctor perspective because this is actually not just an AI assistive tool that helps basically count cells or identify some visual features in a predefined way, but that's actually autonomously taking action without even potentially needing a human. Of course, it's many years until such systems would be used in clinical routine, but I think it's just fascinating that the available technology of large language model has suddenly unlocked such systems and made it feasible to explore this. There's, of course, many people writing about agents now in healthcare. There are some beautiful publications about agents in healthcare or in research. One interesting subfield is the idea of having multi-agent systems. So people are basically proposing that you can take different instances of an LLM and prompt them to different roles. Like you have the nurse LLM, the doctor the oncologist LLM, the surgeon LLM, the pathologist LLM, and they're all prompted to different roles and then talking to each other and coming to a conclusion. Well, I think this is absolutely fascinating, but it's still not, I think, shown with good evidence that this is better than just having, one single agent. Because if you have multiple instances of the same LLM, then you don't actually need these instances. Then it would all also be in one represented in one LLM. But so this is the field of multi-agent systems is absolutely interesting. Where it becomes really interesting is where you have agents agents at different sites talking to each other. For example, imagine two companies each running their own contracting agent, and then they are basically talking to each other to perform any contracting. And this is actually what is happening right now. There was this agent-to-agent protocol released recently by Google and many other big players in the industry field. So people definitely have this on their radar, and our world is moving in towards such an agentization or agentification of many processes. Just a fun fact on the side that there is some interesting legislation being discussed in the US right now, where there's a law being discussed in the House that artificial intelligence that would allow for AI systems to qualify as a practitioner eligible to prescribe drugs. Of course, the technology that they're talking about is agents. I'm not sure. Well, we cannot be sure whether this will make it into law actually, but it's for sure a very interesting proposition. And just the fact that people are discussing this, I think, shows how far our field has come. Let me show you briefly AI agents in cancer research. So it's not basically replacing the jobs of doctors now, it's replacing your jobs or our jobs as researchers. And I'm just half kidding because agents are really good at doing some tasks that we typically do in our routine. For example, we have built a pipeline called Stamp that was built by many people in my lab, including Omar El Nahas and many others. Where you take a set of pathology slides, you take some kind of ground truth for them, and you train models to predict properties from the slides and then evaluate it on others. I know that, of course, everybody knows the world famous TIA toolbox, which was built from the TIA Center, where you can also use a predefined pipeline to solve certain problems. Well, now imagine that it's not a human using this pipeline, but an LLM using this pipeline. And this is absolutely feasible, and actually building a prototype for this can be done like very, very easily, where you basically give an agent access to write and execute code and give it access and show the capabilities of TIA Toolbox. Well, then the toolbox will be used by the agent to solve a high-level problem that you define. So I think that actually in the future, probably most of our software will not be used by human users, but by agents. And so we should also be aware of this and evaluate this together to see how the results differ in comparison to human users. Well, we have recently, this was just a conceptual paper, right? Nothing real, but we have recently described how cancer research could look like in such agentified workflows. The next step would, of course, be not just being in the realm of the virtual realm of computers. Basically computer-based research, but also interacting with somehow with the physical world through robots, etc. This is not my field really, but there has been some very, very interesting research in this space, which I would encourage everybody everybody to look at if you're interested in this. Let's get back to this example in data science where what, for example, our pipeline, our standard approach is we have a small data set and a certain question, and then we use a foundation model and other software tools to get the response. For example, imagine you have 500 slides of lung cancer patients and you know whether they responded to immunotherapy and you want to predict this, right? Well, this is the workflow that we usually take. And just to really make this very explicit, where the agent comes in is actually right up here. So the agent can use the foundation model and other software tools to basically address this question. But the good thing is that the agent also works. I mean, potentially nowadays the agents still need quite a bit of babysitting, but they if they're increasingly capable, increasingly autonomous, they can also iterate faster than we. So what makes a good agent? I think there's basically three different pillars here. One is knowledge. An agent needs knowledge. So, for example, if you want to build a computational pathology agent, you should give it access to the TIA Toolbox manual, right? And all the README of the and etc. If then the agent, of course, is only smart if the LLM is smart, the LLM at its core. So LLMs are now, however, very cheap and very, very smart and run on consumer hardware. So we build most of our agentic workflows through like the OpenAI API, but you can use other tools. For example, we have also many local models running here locally. They struggle still a little bit with the tool use part, but otherwise are very good. And I, of course, love this weird Twitter bubble where people are running like huge open source models such as DeepSeek R1 on clusters of 8 Mac Minis, for example. Also, agents need, of course, really good tools. Ideally, for example, for an image analysis agent, you would want it to have access to the TIA toolbox as a tool. But but sometimes these tools are not really readily available in a format that allows the agents to use them. So Georg Wölflein from my lab has built this has this very nice project called Toolmaker, where he has built an agent that turns any GitHub repository, scientific GitHub repository, into a new tool, and then run it. So please take a look at that. As the very final thing, I just want to show you some general purpose agents such as Manus. We are playing around with these, and they can create like very nice. They are very good for some like tasks such as compiling information from the internet or at making a website, but still, of course, they're not usable. This is not usable for science. So for any scientific workflows, we still tend to build the agents ourselves. With that, I'm basically at the last part at the end of my presentation. I think that there's many questions that we need to think about considering the availability of this technology. One is, of course, the laws that we want to give to these agents, like the guardrails, etc. Also, what do we optimize for? Do we want an agent running TIA toolbox to basically use up all of the UK's electricity in an attempt to get the performance from 90% to 91% or not, right? I mean, there's many different ways how we can think about the objectives and the guardrails. And also, I still think that our domain knowledge is not worthless. I think our domain knowledge is still very important. If you're interested in discussing these topics in more detail, please consider to submit an abstract to our first ESMO AI Congress, which will take place in November 2025. We are very interested in in anything that has a cancer or oncology connection, specifically image analysis, computational pathology, biomarkers, also large language models and agents. There's place for 1,000 people here at this conference. The abstract submission is open. You can submit abstracts. Deadline is in September. I think it will be a very interesting event with also a lot of industry there. I think this would be of potential interest to basically the TIA team and all friends. And with that, I would like to thank you for your attention. I would like to thank my team here in Dresden in Germany and in Heidelberg in Germany. We are about 35 people, half medical doctors, half computer scientists, engineers. Some of them are somewhere in the middle or dual qualified. We do have open positions for software engineers and postdocs. So if you are interested, please reach out. And with that, thank you for your attention, and I will be happy to discuss with you if you have any questions. Thank you.
Well, thank you so much for a really fantastic talk. I really enjoyed the part that toolmaker at the end seemed like a fantastic initiative, and yeah, enjoyed all the TIA toolbox shout outs too. So yeah, does anyone in the room or does anyone online have any questions to start us off with? Yeah, so Mustafa in our group's got a couple of questions he'd like to start with.
Can you hear me, Jacob?
Who's there? Hello?
I tried to get a bit closer. Can you hear me now?
Yes, I can.
Hi, Jacob. It's Mustafa. Thank you very much for the great talk. Really enjoyed the talk. I have several questions. I try to ask them one by one, and so people can get a chance to ask other questions in the middle of my questions. So you talked a lot about the great LLMs that can generate reports, can suggest treatments or agents that can basically do everything. And some of them actually outperform specialists. More and more of these models coming to life, right? But how do you envisage using these tools in future in clinical settings, right? So considering the regulation and responsibilities, as a human being, if I'm a patient, I'd rather a human to judge my case, because in that case, if there is something goes wrong, there is someone to be responsible for it. If agents are going to do everything, I don't know how that tends to be. So I mean, you're an oncologist. How do you see these to be used in the future? Also considering the fact that they can pose some biases, like anchoring bias, right? So they give a wrong suggestion, and that can anchor the oncologist toward the wrong suggestions too. So how do you think they will be used practically?
Thank you very much. Yes, indeed, I'm a human doctor, so I actually would like to keep my job, and I do not endorse agents taking our jobs, right? But I mean, there's two answers to your question. One is, how are these models actually being used right now? And the thing is that they are being used right now, especially here. This is a study from the NHS, where they found that 20% of GPs in the UK use ChatGPT for daily tasks, right? And this is 7 months old, and it's likely underreported, so I would set this number much higher. As you said, ChatGPT or any other large language model is not approved as a medical device as of now, right? So they clearly fall under the definition of the medical device. So in the European Union, they would need a CE mark to be used in clinical routine. Well, they don't have this, but still they are being used. So I think the answer, one of the answers to the answer to one of your questions is that people are already using it now. So we have to think about it. We have to think about how to deal with that, right? I would much rather have regulated, fully proven agents to be used than basically a Wild West scenario where everybody just uses ChatGPT on their private smartphone. Yeah, that's the situation we just have to face. Ultimately, I would also prefer at the moment to be seen by a human doctor, although I must say I have also out of interest used, of course, large language models for basically just out of interest, not on my patients, of course, but either for self-diagnosis or out of academic interest for certain tasks, and they perform very well. I think one last comment here is that the bar of the medical doctors is actually pretty low if you talk about biases, or if you talk about hallucinations. Well, if you actually go and measure how many biases and hallucinations there are with human doctors, then you are, I think, shocked. Having worked like in many different areas of the hospital, I can definitely tell you that there's a lot of hallucinating going on, and it's not always in the best interest of the patient. So we should also always compare them really to the status quo, because they could, even if they're not perfect, they could still outperform humans in some ways.
Yeah, thank you.
So, sorry, Mr.
No, go ahead. I'll just go in between because
Sorry, there's just another question in the chat that I just want to read. That whether large language models can generate new knowledge from the knowledge they have, or they are very good at repeating, summarizing something that they have read somewhere else. Well, I don't know, to be honest. I don't know if it makes a difference, to be honest. Well, so far, large language models have failed to come up with like a way to enable room temperature superconducting, or the universal cure for cancer or whatever. But these are just very difficult problems, right? I think even if they're not, I'm not sure what humans can do in this space. And also, irrespective of this question, I think that these models can be really useful for many things, even if they would never be able to generate new knowledge. And I'm not fully convinced that this is a limitation for them, but certainly a super relevant question. Thank you so much, Carlos.
Thank you. I think a bit of a follow-up question, I suppose, to Mustapha's question. So how far off do you think we are from AI agents actually being utilized in, say, MDT scenarios, as opposed to just individual GPs using ChatGPT?
So I think we are several years away from this because of practical hurdles. I mean, here in our healthcare system in Germany, our preferred way of transmitting information is still by fax, right? So it's a long way to go, but these are just operational and practical hurdles. It's a bit like in digital pathology, right? Where we've had these beautiful solutions for quite a while and nobody's using them because the pathology departments are not really digital. So again, we are seeing that the main battle to fight is the digitalization and the practical workflow readiness.
Thank you. Do you have any more questions from in the room or from online?
Questions?
Mustafa.
Yeah, sorry. I need to turn on my camera. So, yeah, so Jakob sees who's asking the stupid question. Sorry. This is a kind of a question for myself and my peers in the room, really. So, what would you suggest for a future oncologist or a future data scientist not in research, not in academia, but like in industry or people who want to go into market, like what would you suggest them to learn so they have a space in the like to equip themselves very well for their future career? Or what would
Excellent question. Yeah, how do you make yourself agent proof? And the answer is very difficult. I mean, what if you are like a marketing manager and your daily job is to put out tweets and Instagram stories or whatever, then it might be very difficult to make these things agent proof. Also, I mean, this is being asked for other jobs, for software developers, where you already now see that on like freelancer platforms, the demand and the prices are going down in certain circumstances, right? I think we just have to ask ourselves the exactly same questions as other professions. But I think I personally am very optimistic. I mean, if you're really good at what you're doing and ready to learn, then I think there will always be a need for humans, unless, of course, we think like 10 years in the future or so, where we probably cannot predict really what's going to happen.
Yeah, thank you very much.
We've also got a question from Yuri online, who says, "Hi Jakob, question about agentic workflow you use at the department. How do you manage short-term, long-term memory in your workflows, especially given potential higher costs?"
Thank you. Very interesting question. And to the honest answer is we have not optimized this. We have not optimized this yet. For the costs, I think we try to use as small, lightweight models as often as possible. So Llama, like the small Llama 3.38 billion runs on my MacBook Air. I think this is really fascinating, right? The 70 billion one runs on my MacBook Pro. Even that is super fascinating. So with these lightweight models, cost is not is usually not prohibitive. With the bigger models, of course, it is. For the memory, we should benchmark it. We have not, to be honest, we have not done this. Thank you, Yuri.
Thank you. I suppose my next question is, so with foundation models, with the sort of rise of foundation models over the last couple of years, we've sort of struggled a bit more. We've sort of lost a bit of interpretability or explainability into the models, and we often end up using hotspot analysis in our workflows to try and add some sort of explainability. So with the sort of the rise now of going towards AI agents and having so many more different components, how do we ensure that we keep that we can still, how do we ensure explainability or interpretability? Other than by directly, I suppose.
Yeah, we should. I mean, we have to develop the methods for that. Ultimately, it had we have the methods. I think there are some methods available, but we should work on them. Of course, it's still a matter of debate whether you actually need any explainability or not. I think certainly the way to achieve explainability is not to use underpowered models. I mean, we cannot go back to logistic regression in the age of agents just because we think it's more explainable, right? I mean, that's obviously not the way to go. Yeah. In general terms. Yeah.
Sure. Thank you.
Thank you.
I think we have another question from Mr. Bear.
If that's okay. If no one else has any question. So I'd like to go back to the first slide, right? So you mentioned there is a plateau in, the kind of research that's being done in recent years. Can you still hear me?
Yeah.
Okay. So in what aspect really did you mean about the plateau? If it was like less number of research in that area?
Sorry, the performance that was being reached for many tasks, that it's plateauing. So if you have our favorite case to predict microsatellite instability from colorectal cancer from pathology slides, well, now people have used tens of thousands, have trained models, have used foundation models, have fine-tuned them on tens of thousands of patients in a supervised way and have obtained a certain performance. Well, I don't expect this performance to increase again by a lot, right? I think in these cases, for many of the things, many tasks have saturated. Of course, there's still an uncountable number of tasks that we can still address, certainly in rare tumor types, etc. But just like beating the AUC by the next 0.01% on some of these common tasks, I don't think that this is going to happen for some of these.
The thing is, you're completely right, and also wanted to raise the same thing, right? I don't think they're solved yet. Do you think like? I mean, yes, there has been some improvement, especially with the introduction of foundation models, right? But still, the sort of AURCs that you get for some, well, I would admit, really hard questions in computational pathology, they're still very low. And actually, some of the domain-specific models, the first category that you introduced, they may actually work better. If you also take into account the amount of compute that you would need, they might actually be a better choice, don't you think? And well, if you also want to look at it as you know, as a part of an agentic AI, well, you mentioned an agentic AI needs to perceive first, right? In my own opinion, we don't have any good perceiver really. We don't. I mean, we are doing fantastic stuff in computational pathology, yet we don't have a single model that can reliably do cell detection or classification across different types of tissue, or when it goes to a new, slide from a new center, it doesn't fail miserably. So, what's your thought on that?
I think that for many of these tasks, it's a bit frustrating for cell detection or any of these tasks that we never reach like 100% with concordance with the humans. But of course, humans, I mean, human iterator variability is also always higher than we would expect. And in the end, I think we should think about what are actually the things we care about. Does it really matter? Like, do these small differences really matter? Are they really relevant for downstream questions? And I think for many of the tasks that matter, we now have very good, very robust models, especially with foundation models that generalize sufficiently well. To be useful for these downstream tasks. And then I fully agree with you that these should be part of my pitch is basically to go away from having one large, huge multimodal foundation model that does everything. It's more about emphasizing the role even of the small, well-validated tools that we have at our disposal, because an agent can then pick and choose from this toolkit.
Yeah, makes sense. Well, thank you very much again for the great talk.
Thank you. It was a pleasure. Thank you very much. If you have any questions, please reach out to me. And I hope we can see each other also in person again soon at ECDP. Hopefully, whoever is going to ECDP Barcelona, please reach out.
Yeah, I think there's a large contingent of us from TIA going, so yes, we'll hope we see you there. But no, thanks again for a really fantastic talk. It was really, really interesting. And yeah, thank you everyone online and everyone in person. And yeah, see you at the next seminar. No, thank you very much.